apocalyptic visions of armies of robots taking over the world and enslaving the human race. Technology today is indeed progressing at an ever-growing rate. A pocket calculator can solve problems in a matter of seconds that a human would take much longer to do. Many of our mundane and repetitive jobs are now being taken care of by machines. But could a computer ever truly replace a human? Could it enjoy the Northern Lights or fall in love and write a poem? I am Ankita Anirban, and I am speaking to Sir Roger Penrose, Emeritus Rouse Ball Professor of Mathematics and Fellow of Wadham College, Oxford. Although a mathematician at heart, he has made extensive contributions in the fields of physics, philosophy, and even art. He is the recipient of many awards and prizes, including the 1988 Wolf Prize for his work on black holes. His book, The Emperor's New Mind, and its sequel, Shadows of the Mind, explore the idea of artificial intelligence and whether the human mind could ever be fully replicated by a computer. So, do you think that the human mind can ever be replicated by a computer?
I don't, actually, but we have to be careful about the terminology. I mean, I think that the conscious aspects of the human mind, human mind you may include unconscious activities also, but what's involved in consciousness is not to do with computation. And that no matter how complicated the computation is, it would not evoke consciousness, nor would it be able to do the things that I believe consciousness actually is used for. So I think of consciousness as something which actually does affect our behavior. Some people refer to an epiphenomenon, which means that it just happens to tag along. If you have a computational action, for example, or some kind of action, and consciousness sort of comes along as a passenger. I don't take that view. It's more an active role that it plays. I'm not quite sure I could define that in any way that would make a philosopher happy. But nevertheless, I do think it's an active role, and that it's serving a purpose. So that the evolution of consciousness in us and in other animals is, in my view, something which had a strong selective advantage. So that's why we have it, if you like. But that it's not something that a computer does. And the reasons I have for believing this mainly come from mathematical logic. So although there's arguments which I've been trying to make for a long time, first in The Emperor's New Mind, and in more detail in my later book, Shadows of the Mind, but in many other writings, I have tried to make the case that I think is actually a strong case, that there is something quite different that we use our consciousness for, which is not something that could be actually done by a computer as such. To clarify that a little bit, I don't necessarily mean that some device made by some mad scientist or sane scientist, some latter-day Frankenstein, say, who could construct some entity out of maybe inanimate materials, which might conceivably be conscious. But it would not be a computer in the sense that we use that word today.
So what exactly would the difference be? What is it about a computer that it cannot have consciousness?
Well, this is the centenary year of Alan Turing, so it's nice to be able to relate this discussion to Turing's work. You see, Turing in the 1930s put forward a very interesting concept which was basically making clear what a lot of other logicians were doing at the time, which was what is a computation. There were some mathematical problems or classes of problems which had been proposed as, can you find an automatic way of solving all these problems? And in order to address that question, Turing had to make clear what it meant to say an automatic process. And he also showed that there are mathematical problems which lie outside the scope of any automatic process. This was part of his initial thesis. This was more or less known already to Gödel, the famous logician. But I think, as Gödel himself appreciated, Turing's way of looking at it made it much clearer that his way was actually encompassing what you really mean by a computation. Now, the idea is that a computation is something which needs no mind to do it. It just goes on automatically. It has rules which it follows, and these rules are made very clear, and they are the basis of what we now understand by a general-purpose computer. So a Turing machine, the notion that Turing introduced in whenever it was, 1935 or something, the idea is basically what we now understand by a general-purpose computer, or an ordinary computer, laptop, idealized in basically three ways. One is it has an unlimited storage space. So it can you can keep on adding memory, if you like, an unlimited storage space, that it can go on indefinitely without ever wearing out, and that it never makes mistakes. So it's idealized in those ways. But when you've idealized it in those ways, you can actually see the limitations, as Turing himself was very clear about. So initially, he I believe, tried to explore how you might go beyond his ideas. I think that perhaps his experiences at Bletchley Park with decoding and realizing the power of electronic computers, he shifted his view and went round to the view that maybe we are just computers in some very sophisticated kind. But I would dispute that. Let me paraphrase Gödel's famous incompleteness theorem in a slightly different way. This is more the Turing way. Suppose you're trying to prove certain statements in mathematics. Now, these are statements which have to do with the infinite in some way. They always have to do with the infinite. You might say, how can we know about the infinite? Well, let me give you a statement which I think you would agree is pretty obviously true, even though it talks about the infinite. If you add two even numbers together, you always get another even number. You never get an odd number. There is no odd number which is the sum of two even numbers. Now, that's a statement about all numbers, no matter how absolutely fantastically enormous they might be. And yet we can perceive, for various reasons, why that's true. If you add even numbers together, you get another even number. Okay, there are much more sophisticated statements like the famous Fermat's last theorem, which is another example of something of a similar character. Now, let's just take simple statements. Okay, when I say they're simple, they may be very difficult to prove, but statements like that, which are to do with natural numbers, the numbers 0, 1, 2, 3, 4, etc. So we know what we're talking about. They're not some highfalutin concept. But the statements about these numbers, such as the still unproved Goldbach conjecture, every even number greater than 2 is the sum of two prime numbers. So if you know what a prime number is, that's a fairly clear statement. Nobody knows whether that's true or not. People suspect it is true, but there is no known proof. Okay, now how would you expect to be able to prove statements like this? Well, you might have some kind of system of rules, axioms, rules of procedure, which, if you follow them properly, you come out with yes or no. Now, the key point about these rules is that they are computationally checkable, so that if I produce an alleged proof, I can put this on the machine and it says, yep, you've done the rules right. Or, nope, you made a mistake there. So that's what I mean by computationally checkable. Okay? So you could put that on a computer. I don't say that it knows what it's doing. It just can check whether or not the rules have been correctly followed. Now here is the Gödel-Turing statement. This is Turing's version of Gödel's statement. Whatever those rules are, let's call them R, capital R, say. These rules R for rules, if I know what they are, I can construct a statement of this kind that I'm talking about, like sums of prime numbers and so on. I can construct a statement which has the following two properties. First of all, it's true provided the rules do not enable me to prove that 2 equals 3. If I trust the rules to the extent that I know they will never enable me to prove 2 equals 3, then this other statement is certainly true. Yet, that other statement cannot be proved using the rules. So our understanding, our insight, can supersede or transcend any system of rules whatsoever. If you give me a system of rules which are meant to be the way mathematicians prove these statements, I can go away and construct, in a very clear-cut way, a statement which I can show is beyond the scope of the rules, yet it's still true. And the key point is knowing that it's true comes from my trust in the rules. So it's my very trust in the rules which enables me to transcend the rules. Now that's a very remarkable statement. It shows that we don't work by rules. Okay, there are various objections you might make. You say, well, we don't know what we are, we don't know what calculations we do, and so on. I don't believe any of those objections really get to the point. Turing's answer, he knew perfectly well that statement, Turing's answer was, well, human beings make mistakes, and that's where our superiority lies. Okay, maybe, but I really don't think that is what makes us superior to computers. You can make the computers make mistakes, that's easy, you see. So I don't believe that that's why we can do certain things that computers can't. And we do them because we understand what we're doing. Now, I don't know what understanding really is, but whatever it is, it's something which computers don't have. When we use computers, and we do it all, we can make them play chess, we can make them do calculations, to do wonderful simulations in science and so on, but the computer doesn't know what it's doing. It doesn't know, it churns out an answer. It may say yes or no, it may say bishop takes knight, but it hasn't the faintest idea what it's doing. It doesn't understand what it's doing. It's the understanding that enables us to transcend the rules. If we understand the rules enough to believe them, that same trust in the rules enables us to transcend the rules. Now that's very clear what Gödel proved, and Turing's version, he stated in terms of computation. It's the same Gödel's theorem. I could even prove it to you. It's not that hard to prove, this statement. Okay, it's a little bit contorted how you do it. It's not that hard to prove. Now, when I learned about this, not quite in the form I've said it here, when I was a graduate student at Cambridge, before that I probably would have believed that we were all computers in some form, you see. I was that much of a materialist, if you like to use that word. But after hearing about the Gödel theorem, after hearing this from a logician, a lecturer we had at Cambridge, it seemed clear to me, okay, there's something else going on in our heads. And I do believe it's something in our heads. It's not something which comes mystically from outside. I mean, some people might think that. No, I believe it's something to do with the goings-on inside our heads, which is not computational. Now, I had believed this for many decades, but when it came to... I had the idea that someday I would write a book for the general public, you see. I just had this ambition. Maybe long after I'm retired I will have time to do this, you see. But I heard a radio talk where Marvin Minsky, who is a very, what we call strong AI person, who believes we're all computers, and Edward Fredkin was another character of the same beliefs. And they were arguing things which seemed to me to be quite extreme. Like, if you walk from one end of the room, the other end of the room, there are two computers communicating with each other. In the time you walk from one end of the room to the other, they have communicated more things to each other than the human race has ever done in its whole existence, you see. So I said, well, I see where you're coming from. If you take the view that all we do is computations, yeah, I suppose I can see your logic. I don't believe it, because I don't think that's what we do. I think understanding is something which is not a computational process.
And that's what makes us different from computers, then?
Yes. Well, there are lots of things that make us different. Now, I think, feelings, emotions, artist appreciation, but I'm only concentrating on this one quality, which is understanding. And there, I think you can make a good case that what we do is not computational.
So do you think that science can fully understand the mind?
I think it's possible. Now, you see, here's where it's much more speculative. I think the Gödel statement, despite the fact that many people argue with me, and you'd be surprised how many rude things they say, but it seems to me the argument, when presented clearly enough, is absolutely clear. Okay, they say, well, we don't know what algorithm we follow in our heads and all this. It's some very complicated algorithm which gives true mathematics. I find that completely incredible, because you have to say, how did we come about? Well, natural selection. Natural selection didn't favour people who are doing sophisticated mathematics. It's quite other things. It favoured understanding. It favoured consciousness. And consciousness, in my view, is a crucial ingredient to understanding. But if you ask me, do I think science will ever come to grips with that question, I think quite possibly. Whether we properly, completely come to grips with it, I don't know. But I think we shall make progress on that. But I think that the progress will come from trying to understand what in physics there could be which lies outside computation. Now this is where I get, people have trouble agreeing with me sometimes. They say, well, we know all about physics, enough about to handle the brain, where we know all the equations of Newton and Einstein and Schrödinger and so on, and these equations. Okay, we don't know the full details, but they're all things we could put on a computer. We could make a computer, maybe a bigger one than we have now, and feed all the equations in and make it. So we just compute it, aren't we? So I say, well, it's true, although there are little problems here. There are little problems which I'm going to say are not probably the important one. One of them is the very notion of computation depends on discreteness. You have bits which can be this way or that way. Whereas almost all the equations of physics we know about are continuous. They depend on continuous parameters. Newton, still true. Einstein, still true. Schrödinger, Maxwell, all those equations depend on continuous functions. I'm saying, okay, that's true, but maybe that's not really the point. It could be, but I don't believe it. I think that you can simulate with discreteness close enough to the continuous that probably that's not the answer. Is there anything else we don't know in physics? Yes. There's this also I learnt when I was a graduate student at Cambridge doing something quite different from my real research at that time. I learnt from Dirac about quantum mechanics, the great quantum mechanics physicist, and it stayed with me. There's a big paradox in quantum mechanics. It involves two completely different procedures. Let's call one the Schrödinger equation, which it is. I use the letter U for that. That's unitary evolution. That's the word they use. And the other is what you do when you make a measurement. And then you have to do something quite different, which is called the collapse of the wave function, or the reduction of the state vector, R for reduction. So U and R are the two processes. If you look at them carefully, they're strictly speaking mutually inconsistent. If the world works according to U, you can't have any R. Yet you do have R. To me, that says the equations aren't right. Okay, they're very, very good, but they're not quite right. And when they apply to big enough structures, there's something new comes in. And Schrödinger himself was very clear when he made it. He talked about his cat. He said, well, I won't do it because I'm a nice, humane person, but I could have an experiment in which a cat is put in a superposition of being alive and dead, and that's absurd. I mean, he didn't quite put it like that, but basically what he was saying is my equation, when I say my, I'm Schrödinger, you see, Schrödinger's equation doesn't explain what happens to cats. There's something missing. And I agree, there is something missing. And it's that missing thing which has to be involved in our mental processes, in consciousness. It's not just that quantum mechanics is involved in brain action. It's the missing boundary between quantum and classical mechanics, which we don't understand. And when we have that, we might see that it's a non-computational process. And maybe we can see how it works in the brain, maybe we can see why it relates to our feelings and other things about consciousness. So I think it's possible we will make genuine progress. I think we're enormously far from it right now.
In your second book, Shadows of the Mind, you talk about microtubules in the brain. Do you think that any new physics, perhaps non-computational new physics, might play a role in microtubules and how these work? And do you think research in this field may take us a little closer to understanding consciousness?
I don't know what this new physics is that will go beyond quantum mechanics, but I do make a guess. When I wrote The Emperor's New Mind, I couldn't think of any place for this new physics to play a role. I wrote my book anyway, thinking that by the time I'd written it, I would see what the answer was. No, I didn't. However, I was expecting, young people maybe to be stimulated by my book. I'm not sure how many were, but occasionally a scientist would be. And Stuart Hameroff, I had never heard of him before, told me, he wrote me a letter, they used to write letters in those days, in which he pointed out that there was something I evidently didn't know, namely microtubules. There's little tubes which in all cells, almost all cells, not quite all, they have a special role to play in neurons, he says. He knows about them because he puts people to sleep. He's an anesthesiologist. But unlike many of his colleagues who just put people to sleep and wake them up again, he's interested in what he's actually doing. What is he doing to the brain when he puts them to sleep? So he wants to know what qualities of the brain, what structures in the brain do the general anesthetics actually affect. And he comes up with a view that the microtubules, neuronal microtubules, which have different kind of organization from other cells. And I was most impressed by this. I'd never heard of them, stupidly. And it seemed to me, well, here's a chance. There are structures with a great deal, almost crystalline structure, highly organized little tubes. I thought there's a much better chance than neuron propagation, which gets lost in the environment. That's hopeless. But the microtubules, maybe. Now, this has been in a maybe state for a long time. But only within the last couple of years, an Indian scientist who shares your name, Anirban Bandyopadhyay, who has works in Japan for many years with some Japanese colleagues, has been doing experiments on live microtubules. These are actually pig brain microtubules. It's some problem they have getting human ones. But anyway, pig brain microtubules. And he has exhibited some very remarkable quantum properties. So they have very strange properties, high conductivity at very specific frequencies. You measure the resistance with a certain frequency input, and suddenly they become very conductive. And there are different frequencies. There are about 8 different channels or frequencies all working together in some complicated way. But he argues that this has to be a quantum mechanical process. You can't understand this from purely classical ideas. This is the beginning of some research, but it's a new area which I think could be extremely exciting and maybe tell us something very important about what's going on in brain activity, which could be related to what's really going on in consciousness.
And is this non-computational?
That's very hard to tell. At this stage, we would only be looking for coherent quantum effects. In order for there to be any chance for the new physics that I claim is there to come in, you need many, many microtubules actually acting in concert. There's not enough displacement of mass. See, the criterion that, as I say, this is a man named Diyoshi and I who've independently put forward a proposal that if you have enough displacement of mass between two states, then that gives you a lifetime for how long that superposition can live. So if you have a superposition of two states, you can work out a lifetime. It can't last for longer than so on. It becomes one or the other. Now that lifetime for a single microtubule will be enormously long. So that can't be in itself what gives consciousness, because conscious actions occur in matters of fractions of a second. So one is looking for many microtubules acting together in some coherent process. So you would need lots of them acting together. But it's a beginning. You can't tell from just that experiment that there's anything non-computational going on. It's not even at the level where the new physics would come in. It's at a level where quantum physics seems to be playing a role, at a level where people thought couldn't happen because the temperature is too high, and you need low temperature or isolation or both in order to get coherent quantum effects. And he seems to be seeing coherent quantum effects at high temperatures, body temperature or higher than body temperature. And there's a good step, a beginning. It's only a beginning. You need lots of microtubules coherently. You need to understand about the structure of the brain. You need to understand all sorts of things. It's a huge story, I'm sure. But at least it's perhaps a little window into what's going on.
Yes, thank you very much. Hello.